I will talk about the grid theorem for vertex-minor, which is a quite interesting result on the vertex-minor theory. So this is a joint work with Jim Geelen and McCarty from University of Waterloo and Paul Wollan from the University of Rome. So I think probably most of you know about the grid theorem. The grid theorem says that for every planar graph, every graph of sufficiently large trees contains this graph as a line. So there are lots of application of grid theorem, and then it's also the main part of the structure theorem for H-free graphs. Also, the one simple characterization from this theorem is that the H-free graphs have bounded trees if and only if H is planar. But we try to think about what kind of thing can be possible for dense graph. So is there some dense analog statement of this? So we have the parameter, right? Rank width and click width and so on. So probably, so can you obtain some structure in the every graph of sufficiently large rank width or click width? So this is the motivation of this question. But before going to the statement, the circle graph is important graph classes in this talk. So I want to introduce at the first moment. So the circle graph are the graphs that has a circle representation. So what is a circle representation? So you have a circle and then you have a set of chords in the circle like this. There are 4 chords there. And then each chord corresponds to a vertex of the graph. And then they are adjacent depending on if they intersect, the corresponding chords intersect in the diagram. So it's well known that the circle graphs have unbounded rank width. So you can compare to the planar graphs in the tree width case. The planar graphs have unbounded tree width, right? So here the circle graphs have unbounded rank width. So if you don't know the rank width, I will give the definition of rank width and later. But the rank width is just the decomposition, the width parameter that captures the dense graph classes. And interesting fact is that the circle graphs are closed under certain operation called the vertex-minors. So what is the vertex-minor? So vertex-minor, if a graph H is a vertex-minor of some large graph, if you can obtain by a sequence of 2 operations. So one is that you are allowed to delete the vertices, and the other is that you take local complementation at vertices. So to take a local complementation, so you look at the neighborhood of V, and then you swap the adjacency relation inside of the neighborhood. Like previously you have an H between them, then you remove a H in the resulting graph, and then there was no H between them, then you add an H. So this is an operation called the local complementation, and then you only allow these 2 operations to take a vertex-minor. So why the vertex-minor is interesting? So it looks like local complementation is a weird operation, but it's very natural in the circle graphs. So actually, Boucher observed that this local complementation preserved the circle diagram. So I want to see here. So I want to take in this graph, I want to take a local complementation at B, and then the resulting graph looks like this. But I can take a code diagram of this circle diagram of this graph from the code diagram of the original graph. So what you do is that so you look at the chords B and then take one part of the arc divided by endpoints of B. And then you just read the order of the endpoints, and then you swap the order of the endpoints up there. So here, so A and D and C appears in the order, right? And then you swap the disorder. So you put the C in the below, and then D and A. And then here you just take in the same as before, and then you link chords again. But then what you can see is that if you look at the neighborhood of B, which means that the chords crossing into these two parts, right? And then previously they were adjacent, then this become a non-edge because in the one part you change it, the order of the thing, and then previously there was no edge, then they become an edge after appliance. So this local complementation preserved this circle diagram. And so circle graphs are preserved by this local complementation. Also, deleting vertices should preserve the circle graph. So it's like a very similar situation, like planar graphs are close under taking minors, and then planar graphs have unbounded trees. So it looks like circle graphs have an important role in the world of rank quiz. And actually, what it proves is that if you fix any circle graph H, then every graph of sufficiently large rank quiz should contain this graph H as a vertex minor. So, yeah. So this gives a same characterization where if you forbid some fixed graph H as a vertex minor, then the class has bounded rank quiz if and only H is a circle graph. So if you exclude any non-circle graph as a vertex minor, then you contain all circle graphs in the class. So it has unbounded rank quiz. Yeah, probably I have to introduce the rank quiz, right? Probably some of you don't know the rank quiz. So the rank quiz is that it's a user graph decomposition scheme. What is you know, you have to know the function rank function here, and then when you take a vertex set of a graph, and so you look at the sub-matrix of the adjacency matrix, where the rows are indexed by S, and then the columns are indexed by the rest, and then you put the 1 if the corresponding vertices are adjacent, and 0 otherwise. And then you compute the rank of this matrix over the binary field. So for instance, if you have this matrix, the rank is 2 because this like 1, 0, 0 plus 0, 0, 1 is 1, 0, 1. Right? So rank is 3. Sorry, yeah, 3. Right? So it's not 4. I think. So basically, what you want to do is that you want to count the number of distinct rows. So you want to count the number of patterns between the partitions. So this is what you want. But why we use the rank is that the rank function is a submodular function. So this gives some nice idea to generalize for tree width and branch width in the sparse graph. And the rank decomposition consists of trees whose all internal vertices have degree 3, and then you have some function from the vertices to the leaves, and then for each edge you give a partition of the vertex set, right? And then you measure the rank function, and then you take a width of E as this value. And the width of this decomposition is the maximum width over all edges, and then the rank width is the minimum width over all rank decompositions. Is there any question about the rank width?
Can you just again what is the rank decomposition?
Sorry?
The rank decomposition?
So rank decomposition is the pair of a tree and then the bisection from the vertices to the leaves. So this is the rank decomposition. So for one fixed rank decomposition, so you can measure the width of each edge. So width of edge is that this edge partition the vertex set into two parts, right? Because it's tree, right? And then you compute the rank for the one part. Yeah. So basically the rank width is small, means that you can recursively partition into two parts, where the number of patterns between them is small. Right? Pattern means that they are the same neighborhood. Yeah. So basically, I want to prove this theorem, and I want to sketch out the proof of this result in this talk. So the proof consists of basically four parts. The first one is that we devised the concept of comparability grid, which is corresponding to user grid in the planar sense. We proved that every circle graph is a vertex-minor of T by T comparability grid, which I will introduce later. And so we don't work every circle graph individually. So we just want to construct a comparability grid. The second part is that we prove some disentangled lemma, which basically argues something on the two vertexes, that if they have a small rank between them, but the connectivity between them is large. So it's like a McCarty theorem. So like in the McCarty theorem is that you have two vertexes and then connectivity is large, then you have disjoint passes, right? But you want to find some construction from this assumption. So this is the second part. And the third part is that we introduce some intermediate construction, which we can obtain this comparability grid. So we will see that so it's the original, the full definition is quite heavy, but I will just give a picture of this constellation, and then
Second part, the connectivity is a usual graph.
the rank function. So when you have two vertexes A and B, so the connectivity means that so whatever you take a vertex partition containing one part containing A and the other part is B, the rank is it's like a linking theorem. But the second part is actually the original paper by Sang-il. There is a theorem that if you have a connectivity is large, you can take some vertex-minor. But we cannot easily use the theorem because the theorem doesn't guarantee that the x and y are stay same. So we have some construction on the x union y, and then we don't want to change the x union y. But, so our theorem will test that we stay the x and y in the same. Yeah, so this is something. And then just the last part is that you can extract some comparability grid from this intermediate construction. Okay, the first part is that the circle graph and comparability grid. Yeah. Probably this is the most elementary part of the yes. So this is the comparability grid. Yes. So if you don't forget this circle diagram, so just you put the n by n points in the grid way, and then you add edges between the left bottom to the right top. So in the same coordinates you also add it. But actually this is a circle graph with this representation. The thing is that usually in the circle diagram you don't allow to have a same endpoint, but actually you can slightly change the endpoints so that you don't have same endpoints. But in this picture it's better to take this one, so I just keep it. And it's hard to say that, hard to observe that this has this representation. But for instance, if you look at this code A1BC, so this meets every other code, right? So A1BC code will correspond to the 1, comma 4. And then the A1.
A1BC intersect with A3BC?
Yeah, because in the BC.
So, also if the A3BC is the...
Yeah, we count as the same. So I will change it so that they are with each other. So A1, B2 correspond to somewhere here. So you can check. So the finding is that do you know the permutation graphs? So probably the permutation graph is that I didn't put the definition. So the permutation graph is the similar intersection graphs, but you have two lines, and So you have two given lines, and then you have a set of lines between them, and then the intersection graph of this is permutation graph. But the thing is that this graph is not only circle graph, it's permutation graph, because you can cut off here and the other point. And then you put the A1 to A1 on the one line, and then B1 to Bn on the other line. Right? So this is the permutation graph. And furthermore, this is actually universal graph of permutation graph. So every graph, any permutation graph is an induced subgraph of this kind of graph. Because, so it's an easy observation. So you have any permutation graph like this, then you put the A1, A2, A3, and A4 in this order, and then B1, B2, B3, and B4 in this order. Then you just take a 4x4 comparability grid. So all the codes are there. So you just remove any other codes, right?
For the vertex-minor, there is no difference between circle and permutation.
Yeah, kind of. Yeah. Right.
Vertex-minor, permutation and circle.
Yes. Yeah, so what you actually prove is that every circle graph on n vertices is vertex-minor over 3n times 3n comparability grid. So it consists of two parts. So one part is we already observed. Every permutation graph on n vertices can be embedded, can be obtained as an induced subgraph of n by n comparability grid. And the other part is that every circle graph on n vertices is vertex-minor of a permutation graph on 3n vertices. So we have to prove the second thing. Yes. Yeah. So before going to this, we really have to think about the local complementation and diagram. So I just remind you that how this affects. So if you apply the local complementation at B, so you take one of the two parts divided by the endpoints of B, and then you swap the orders of the endpoints. And this is called circle diagram for the resulting graph. And so suppose that the circle diagram is given, and then you fix any arc, any sub arc of the chord. So it's just independent with the chords. So you take any arc, and what you want to do is that so first see that we want to call that some chord is crossing with respect to this arc, meaning that the one endpoint is on this arc and the other endpoint in the other part. So the others are non-crossing. Non-crossing means that they lie on this arc, or the other lie on the other. So observation is that if there are only crossing arc, then it's a permutation graph, right? So we don't have to prove anything. So we can assume that there is a non-crossing arc, say A here, right? So I want to make A to crossing arc. So this is the thing. So what you do is that you pick one endpoint of A, and then any point on the other part. Let's say P. So as in this picture, so I pick an endpoint of A here, and then any other point P up there, and then we add to some additional chords near to the endpoint like this. So for this endpoint, you distinguish these two guys, but the other part you just put the close to P. So the observation is that these two new vertices are twins to the every others except the A, right? So it distinguishes the A, but they are twins to all the others. Yeah. So now, if you apply the local complementation in X1 first, then I want to swap the ordering on the right-hand part. Okay, but then you swap the orders inside of X2 in the reversely, and then you put this to the P. But then after applying X2 again, then you can swap the right-hand part of X2 again. so that they are on the same. So after applying these two operations, every other quasar stays same, but you just move A to there. Right? Yeah. So the resulting thing is that you reduce the number of non-crossing arc by 1, right? So you have one less non-crossing course in this way. So you add the two vertices, right? So you have some slightly larger graph where that you have one less course. So you recursive this argument for every vertex. So at the end, so x1, x2 are really a vertex of C. So at the end, you will find the permutation graph on 3n vertices, which contains the original graph as a vertex line. And most, and more.
3n minus 3, like 3n minus 2, maybe. So initially you start with already at least one not crossing.
Yes. You can optimize. Sorry? In the whole object? Because m by n permutation graph, you mean? I don't know. Yeah, as far as yeah, we didn't try to optimize. Yeah, so this is the result that every circle graph is the vertex-minor of this comparability. Yeah. So I want to go to the second part. Is there some more question? Yeah. So the second part is that so we want to describe something between the two vertices, like S and T there. Maybe S and T. And then so we have a large connectivity between them. That one you can obtain. So the connectivity means that like this. So you take so given two sets S and T, so you consider every vertex partition A and B, where that A contains S and B contains T, and then you consider the rank of this, and the minimum of this is of S and T. Yeah, actually, the Sang-il proof in the original paper on the rank-quiz and vertex-minor, he showed that when you have two vertices with large connectivity, then you can obtain a vertex-minor on A union B, where the rank between them is large. Somehow it looks like useful, but so yeah, it's like a Manga theorem where if you have many disjoint passes, then you can contract it into all the other vertices. So to obtain, you have essentially have two sets with matching. So it's similar to the Manga theorem. But this theorem is very difficult to apply for our purpose because this vertex-minor doesn't say about the inside of A and B. So we might change it A or B, but we don't want to do that. So we construct something and then we change this, and then it's very difficult to arrange. So we want to prove something more than this. And before doing this, I want to give a definition of a K-link. Yeah. So you have two sets S and T, and then K-link is the pairs of set x1 and x2 with one of these two types. One is that so you might have x1 equal to x2, and then rank between the x2 to S is the full. So here full means that so we can assume that S and T is much larger than K. And then this full rank means that the rank is just K, because the size of this is K, right? And then the rank between this set to T is also K. Or, so you have these two distinct sets, x1 and x2, and then you have a sequence of a full rank between in this order, but between the S to x2 and then x1 to T is kind of trivial. So trivial here means that they have, so all vertices of xi have a same neighborhood of the T. Yeah. So we want to try to find one of these two things with preserving the S and T. So this is our purpose. So the statement is not that hard. So you have some integer k here, and then S and T are some disjoint sets with actually much larger than k. And then the point is that we have an assumption that the rank between the S and T is smaller than k. So the previous theorem by Sang-il doesn't have any assumption on the between S and T, but here the rank between S and T is small. And then the connectivity is much larger than k. Just assume that much larger than k. Then you can find the vertex-minor G prime, where there's the S union T, you just have the same thing in the resulting graph, and then G prime has the K link for S and T. So S and T are essentially stay same, but you can find something on the outside which is just connected as a full link, full rank. Yeah. Yeah. How do we obtain? Yes. First, observe. Yeah. Is there some question on the statement? Yeah. So how do we obtain this? So first, assume that you can assume to prove this statement, you can assume that there are no twins to the S union T. So for instance, so if you have two twins V and W, then you can throw away V. But it's not that simple because it's just implied by Sang-il's result that so one of these three guys still have same connectivity between S and T. So it preserves a connectivity. So you cannot simply remove but so by this result, you can assume that there are no twins to the S union T.
Two of the three have the same.
Yes, anyway. Yeah, actually it depending on their edge between the V and W, so you have to take two of them or two of them, something. But I don't want to give a detail. And actually, matrix intersection theorem coming here. So I think matrix was given the Nick gave a talk. Anyway, so we consider the linear. So you consider the vector matrix, which on the matrix adjacent matrix between S and this rest thing, and then another matrix on the T, and then the rest. And then the simple observation is that you have a K independent set for both matrix. So this is just the K link of the first type, right? So this means that so you have a K set here where the rank between them is also the full rank. So this is independent means that they are so the rank is K, right? Exactly K, and then also they are independent to T means that they are the full rank. So if there has a K elements for both matrix, then you have a K link. So we may assume that such a set does not exist. This means that by matrix intersection theorem, so you can. So if you don't know the matrix intersection, you just see the result. So you can. So we know that there is a partition of the rest set into the P and Q, such that the rank between S and P is small, and sum of the rank between S and P and the Q and T is less than K. Yeah, there is a min-max theorem in the matrix intersection theorem. It implies this result.
Okay, the sum of this rank is smaller than K follows from that the rank between S and T is smaller.
No, there are no common independence. Yeah, common entity to matrix. The maximum size of a common independent set is equal to the minimum. Yeah. And what you know is that by the assumption, so you have this P and Q, right? So if you consider the cut by taking S union Q and P union T, then this is just the vertex partition between S and T. So it should be sufficiently large by the kappa, right? And so what you know is that here, so if you look at the S and P, it's small, right? And then Q and T is small, and then also we assume that the S and T is small, right? So this implies that the rank between P and Q should be large. Yeah. Furthermore, so we want to, so we restricted this P into this P1 to Pi. So it's just divided by number of neighborhood on the S. So because the rank between S and P is less than K, so you can have at most 2 to the K parts on there, which have the same neighborhood on S, right? Each having same neighborhood. And then also you partition the Qi's to the T in at most 2 to the K. And then because the rank between this is still sufficiently large, you should have the Qi and Pj which have a large rank between them. And then you know that they have a trivial to S and then trivial to T, right? But it looks like almost a K link, right? But still, we don't know about the P2 to T, right? So why the rank between P2 to T is large? This is just implies by that because so we don't have 2 twins to the S union T, right? But all guys in P2 have the same neighborhood on S. So no 2 vertices in P2 have the same neighborhood on T. So basically the rank between P2 to T is large, right? So you can extract, so but then rank is not exactly the same size of P2, but you still have a large rank. So you can just choose basis elements of that and then basis element of Qi, then this become a K.
So and no 2 vertices of Pj have the same neighborhood on T. Does it imply immediately that?
Yeah. Okay. So we know that the Pi and Qj sets are large because rank between them is large. So you have a huge set between them, and then you have a huge set to T where the no 2 vertices have same neighborhood of T, right? So the rank should be large. Because if the rank is small, then so you restrict the number of neighborhood type, right? But the number of neighborhood type is large. Yeah. Mm-hmm.
So we go back to the intuitive definition. The number of neighborhood values. If rank is more than the number of neighborhood values.
Yeah, actually that's true. Okay. If you have one matrix of rank K, then the number of distinct rows is also 2 to the K.
Yeah.
The version of touch linking theorem prove the integrate minor.
Yeah, maybe. Yeah. I think so. So Jim Geelen well know about this thing, so probably the same. Yeah. So what you prove is that you have these disjoint sets with the rank between them is small, but the connectivity is large. Then you can find the K link, and furthermore you have the same graph on the S union. Yeah. Okay. So the third part is that we define some intermediate construction to go to the comparability grid. Yeah. So what we basically construct is in the middle guy. So this is just explanation. So you just look at this part. So you have a huge set of disjoint stars here, where the sets on the centers are independent. And then for between the two stars, the center to the leaves also there are no edges. So you might have only edges between the leaves between them. Okay. So this is the thing. And then you have these two partition into the set of stars. You have n stars on the top, and then the m stars on the bottom. And then you have a connected graph on the n vertices, basically. Yeah, so K is this set. And so what you know is that the construction tells that if there is an edge between them, the corresponding leaves are either matching or the half graph. And then if you don't have an edge, then there are no edge between them. And then for all the other pairs in below, you don't have any edges between them. Yeah. So basically, so you want to increase the size of this n. So you want to make larger and larger between this guy. And then what I proved with Sang-il recently that if you exclude a huge set of disjoint stars, then you have a bounded rank width. So at the beginning, you can assume that there are a huge set of large stars. Yeah. So this is at the beginning, and yeah. So so from that how to connect these guys and these guys, right? So we applied this disentangling lemma between this n parts and n parts. Maybe at the beginning you just cut one thing and then rest. Then in the middle time, so you take some connected part over there, and then you have a rest, and then you look at the partition between them. Because all these guys are large, so by the disentangling lemma, you can find the T-link. The one thing is that why the connectivity is large. So this might be question. So this is so we have to assume that it has a sufficiently large rank width with a minimally vertex-minor minimally. Like the graph has the rank is 2 to the 2 to the 100, but all the proper vertex-minor is not that less than that number. Then you have a result that if you have a huge set, then the connectivity is large. Yeah. So this is proved by Sang-il. So yeah, maybe I have to state that. Yeah. Yep.
So, but where does this constellation come from? Do you just construct this constellation according to some rule and then prove this property, or you find it?
No, this is the definition of constellation. So definition of NMK constellation is that so you have a set of n star, and then you have a set of m star. And then the constellation consists of this H and something and K, where K is some connected graph on n vertices. Where if there is an edge, then the corresponding leaves are connected by matching or connected by a half graph. So this is the definition.
So among m stars, you don't have any edges.
Yeah, among m stars, you don't have any edges. So at the beginning, so all the guys are just m stars, and then you increase the size of m. At the beginning, so my result is Sang-il. So if you exclude the huge set of large star as a vertex-minor, you have a bounded rank width. So this is proved in the other paper. Yeah, so we can assume that at the beginning you have large stars, and then. Yeah, so we will build a grid. Yeah. later. Yeah.
Between the leaves of m stars and n stars, there is no edge.
Yeah, between the n star and m star, there is no edge. Yes.
And between the m, among the m star leaves,
You
there's
you don't have edge. Yeah. Yeah. So you only have additional edges between the n stars, where they connected by this rule. So if you have an edge, then you have a matching or you have a half graph.
WH is a number or what?
WH is for each H, so this set is WH.
Oh, it's a set of vertices.
Yeah, set of vertices. So, yeah. So this is WHI. Sorry. Yeah, that's okay. Yeah, so this is a definition, and then so basically, so what I want to describe is that so how to connect this n star to m star, right? So you want to increase the connected part more and more. So we apply the disentangling lemma, but before doing this, the Sang proved that kind of these things. So if you have a rank list is like a T, where G is T, and then or proper vertex-minor have rank list is less than K, less than T. Then if you have two large sets, then connectivity should be large. Then like so these two sets are the large, implies that the kappa AB is large. Yeah, so here the stars are huge itself. So if you partition into two parts, then it should be both parts are large. So connectivity should be large. So we can apply this disentangling lemma, and then this give some xi between these guys. So this is some T link for some large T. Probably you might have x and x, but I just depict this case. So you have one set x, and then this is a full rank to the whole set, right? Whole set of n, and then this is a full rank to the whole set of n. But the thing is that so I just want to link one star to the other star. So you just pick one star which is full length to here. So because this T is sufficiently large with respect to this n, so you can just choose one of stars which have a full length to here. And then in the same for this guy. And then for other guys, you can just apply the Ramsey to the clean the edges. So you just take a homogeneous between them or full length between them. And then what you do is that in the very simple case, like this is connected by matching to here and connected by matching to here. So you apply the local complementation at each vertex to take down x1 to here, like that. Yeah, this is almost hand wavy, but yeah. So basically, so you want to shrink down x1 to here, so that this guy is linked to this star as a match, like that. But there are lots of cases where this is a half graph or this is matching and x1 and x2. And so, yeah. But at the end, so you increase the size of n, and of course at each time, so you apply the huge number of ranges, so the size of each matching is reduced and reduced. But at the beginning, it takes the huge stars and then you reduce and reduce. At the end, you have some still large star.
So the goal is to increase n.
The goal is to increase n.
Only increase n, you don't care about the graph K.
Yeah, I don't, because, yeah, this is the part for, yeah. Yeah.
But you still keep k to be connected.
K to be connected, that's
K is
important.
increasing as well, right? Because you keep adding one more vertex.
Yeah, K is n vertices, so n is increased.
Yeah,
K is increased.
So I did the graph, you didn't fix the graph K. Just
Yeah, we didn't fix it. Yeah. So we will have some connected graph
So
K.
usually you start with the 1 plus n to be 1.
Yeah, n to be 1. Yeah, yeah, n to be 1.
More and more.
Right.
Maybe and then you apply against it. Okay.
It's the next slide. Yeah. Yeah, so we want to extract at the end, what you do is that, so K is the large connected graph, right? N is large, right? So you can find either long path or large star or large complete graph there, right? So you take those parts and then you want to extract something from there. Of course, there are lots of cases, right? Because H in this graph means that the corresponding stars are connected by matching or half graph, right? And then, so these 3 cases with those options, and then this is heavy case analysis. I want to show some cases. Like this is a simple case where that, so I draw the stars in this way. Okay. So you have these stars where that they are linked by paths, and then in between they are matching. This is induced match, I mean. Yeah. Can you obtain something from this? So actually, this is a very simple case where that suppose you have n vertices, maybe 4 vertices here, and then you have this approaches 2 layers there. So what you can do is that so I want to create any graph on this VIs. So if you want to add the edge between the V1 to V2, so you take a line of G12 from the V1 to V2, and then you just take a local complementation here to add an edge. This doesn't change anything on the other part, right? Yeah. So if you want to add any edges, then you just want to go to the corresponding layer, and then so you shrink down to the edge. So basically, in this case, you can create any graph on this set. Right. For instance, you have, this is a star case, right? So you have this is original stars in the constellation, and then the graph K is a star. So and then each edge corresponding to matching. Then you have this kind of thing. In this case, basically the same. So you take G0 for the J3 there, and then if you want to add the edge between these 2 guys, so you just use this edge. But the local complementation over there doesn't change anything. So for every pair you pick some line there, then you just use there if you want to add an edge. So this is a simple case. So the hard case actually come up with like this. So you have a path over that. So you have a sequence of half graphs, and then so you want to construct the comparability grid, right? So here you need to try something. So you apply the local complementation over these guys. Yeah. So what happens is that if you apply the local complementation here, so you will add all edges between this guy to all these 4 vertices, right? And then so if you apply this guy, then you add an edge from these 2 guys to these 3 guys, and so on. But the thing is that I want to say this as an independent set, right? So if you apply the local complementation, so you change the status between here, so this become a complete graph, right? But when you do the second thing, then you remove again an edges in the complete graph, right? So actually, if you try to do this, then so you can take half of them, which is independent. Yeah. So you take, so basically after taking all of these guys, you can see that you have a sequence of chains where these 2 sets again a chain graph. But by taking half of the rows. Half of the vertices. And then again, if you apply the local complementation here, then you increase the size of this and so on. Yeah. Yeah, this is the most technical point in the paper. Yeah, which I want to skip. Yeah. Okay, so this is the all. So we proved that for every circle graph, every graph of sufficiently large rank list contains H as a vertex-minor. So there are some questions. The application of this is that algorithmic application is that H vertex-minor testing can be polynomial time for circle graph. So if you want to take H as a whether the given graph contains some fixed circle graph as a vertex-minor, so you know that if you don't have a circle graph, you have a bounded rank, right? So there should be some measurable function there. so you just test whether the graph has a rank is larger than this number or not. So if the rank is larger, then you just have this. So otherwise, you have a bounded rank list, and then by the monad of second order logic, you can test the H vertex-minor test. Are there like we just have a grid theorem, so we don't actually think about many applications, but just motivated by the usefulness of grid minor theorem for trees. This kind of thing might be the thing. Like we try to think about the vertex deletion problem for a circle graph. Like you want to delete k vertices to obtain a circle graph. You don't know whether this can be solved in time FPT. Like this is corresponding like a planar vertex deletion, right? In the planar vertex deletion problem, you really use the grid theorem, and then you find the irrelevant vertex to reduce the tree width. So can you do some similar kind of thing here? And also, we can think about the H vertex-minor vertex deletion. Like in the minor world, people really try to work on the H minor deletion, right? So you want to delete k vertices so that the graph has H minor, and then
H minor free or H minor?
H minor free. Yeah. H minor free. Yeah. Maybe I forgot the free here. Yeah. So if H, in that case, if H is a planar, then H minor deletion can be solved in singular exponential time. So can you obtain something similar here? Like for every circle graph, you can do something. So I think just a FPT algorithm can be obtained by monad second order logic, I think. But can you obtain some with the elementary function here? So even I didn't try any small graphs like HSP5 or something. So recently, with Edward Ivan and Robert Gagnon, we proved that distance hereditary vertex deletion is FPT, admits a single exponential time algorithm. And then the distance hereditary graphs are graphs that does not have a C5 as vertex. So this is one, as far as I know, one result, kind of this thing. And so very recently, with McCarty and Paul Wollan, we showed that so actually we devised the concept of depth parameter of rank list, like rank we call rank depth, and so maybe you know the Schwab depth of the graph. So this is equivalent, and then we proved that. So it was conjecture in 2016 with Peter Hillany and me and two other guys, that every class of graphs of unbounded rank list contains a long path as vertex-minor, and then we proved that this very recently. But so we actually don't know much about this conjecture, right? So we conjecture that as for passes, so like in the passes we know that for every tree T, so every graph of sufficiently large passes contains T as a minor. Can you obtain something similar to vertex-minor? Yeah, we try to think about quite a long time, but we don't have much progress. So this is the remaining part of this word, I think. So the much more general question is, can you describe the structure of H vertex-minor free graphs for every H? like H minor fields. Okay, that's all. Thank you.